Hello, my name is Aaliyah Wittig, and I am a math PhD student at SUNY Albany, and I'm going to be talking about Wolff's ideal problem on the multiplier algebra of the Dirichlet space, which is a problem related to the corona theorem. So first we start with Carlson's original corona theorem. Let H infinity be the Banach algebra consisting of all functions analytic on the open unit disk with bounded supremum norm. Lennart Carlson proved the corona theorem in 1962. There are a couple of equivalent statements of the corona theorem. The one we will be using today is the more elementary version. It states that given n functions fj and h infinity such that there exists a positive constant delta such that the sum of their modulus squared is between delta and 1, then there exists n functions gj and h infinity such that the sum of their product with the fj is 1. So what condition C says is that 1 is in the ideal generated by the fj. So B implies that the fj belong to no maximal ideal of h infinity. The name the corona theorem comes from the other version, which defines the corona as the maximal ideal space of h infinity quotient the closed unit disk, where the closed unit disk is identified with the set of point evaluation functionals on h infinity. So this other version simply states that the corona is empty, which was first conjectured by Kakutani in 1941 and of course proved by Carlson in 1962. In 1979, Thomas Wolff gave a simplified proof, which I'll be outlining briefly. So given a set of fj satisfying condition B stated here, we want to construct a set gj in h infinity satisfying condition C. Now, Wolff's proof can be broken up into 4 parts. The first part is a reduction to a d-bar problem. So recall that a function g is analytic if and only if d bar g is equal to 0. We need d bar gj to be 0 so that gj is in h infinity. So we make this initial construction of gj and see easily that it satisfies this condition C. We also have the supremum norm is bounded, but the problem is that d bar is not equal to 0. Right, so how do we go about solving that problem? Well, let's consider adding a function, wj, to make gj analytic. So let's let hj denote our initial guess and take gj to be equal to hj plus wj. So that d bar g is equal to 0 if and only if d bar w is equal to negative d bar h. So we want to find this w satisfying this d bar equation, which will make gj analytic. And we also want the sum of the product wj fj to be 0 so that we still have condition C satisfied. And we also need the supremum norm to be bounded so that the gj is in h infinity. So now a potential solution is found using some algebra techniques, and it's given in terms of smooth functions wjk defined on a slightly larger disk, satisfying this new d-bar equation on the closed disk. So taking gj equal to hj plus wj, our d bar gj is equal to this long equation here, which is equal to 0 by construction, right? So we also have the sum of the wj fj is equal to 0, which gives us condition C, right? So sum of gj fj is equal to 1. Now we must establish the existence of these smooth functions, wjk, satisfying this new d-bar equation, and find a bound for the supremum norm of gj. So part 2 of Wolff's proof is just that, right? Establishing the existence of this wjk. right? So that's going to be given to us through this Cauchy transform. So given a smooth function phi with compact support containing D and a solution to D bar F equals phi is given by the Cauchy transform of phi. And the Cauchy transform phi hat is smooth as well. So defining Wjk as the Cauchy transform of Hj bar Hk will solve our D bar problem. And then part 3 consists of integral estimates and the use of, including the use of bounded mean oscillation and Carlson measures, Green's theorem, and some Littlewood-Paley type identities, right? So this is just, proving this boundedness of these norms. And the part 4 is just the conclusion of the proof. Which is applying the integral estimates in the specific case of this construction of Gj, you see here. Right, so with the simplified proof of the Corona theorem complete, we look at possible generalizations of the Corona theorem. So with the goal of classifying ideal membership, one may ask under what conditions we can replace 1 with an arbitrary h in H infinity. If modulus of H satisfies this inequality, does that necessarily imply that H is contained in the ideal generated by the Fj? Well, it turns out that the answer is no. A counterexample was given by Rowe in 1967. However, it is still plausible that some power of H is in the ideal. Turns out the condition is sufficient to imply that HP is in the ideal for P greater than 2, but not less than 2. So Wolff's ideal theorem sums this up, stating this inequality is sufficient to conclude that H cubed is in the ideal. And it wasn't for another 20 years that the case P equals 2 was proven to also not be true. Right, so that was given by Trail. Right, so the condition is not sufficient to conclude H squared is in the ideal. So now we will turn our attention to more recent work on Wolff-type ideal problems on multiplier algebras. So let's let H of omega be a reproducing kernel Hilbert space of analytic functions on domain omega. Then the multiplier algebra of H infinity is defined as the set of functions in H omega whose product with another H omega function is also in H omega. So the useful relationship between multiplier spaces and reproducing kernels is that for a function phi in the multiplier space and z in the disk, the adjoint of the multiplication operator of phi on the kernel at z is just the product of the conjugate of phi and the kernel at z. So this implies that the supremum norm of phi is less than the operator norm, multiplication operator norm. So the multiplier algebra of any reproducing kernel Hilbert space of analytic functions on the disk is contained in H infinity. And just a couple examples, H infinity is the multiplier algebra for, it's equal to the multiplier algebra for the Hardy space as well as the Bergman space. And we'll see that the H infinity contains the multiplier algebra of the Dirichlet space, but it's not equal to. So the Dirichlet space is a space of all analytic functions on the unit disk whose coefficients are square summable with weight n plus 1. The Dirichlet norm consists of 2 parts, the squared L2 norm on the boundary of the disk and the squared L2 norm of the derivative on the disk. So we'll be concerned with the multiplier algebra of the Dirichlet space, which I'll call MD. And we have this inclusion here where you see that the multiplier algebra of the Dirichlet space is a proper subset of H infinity. So now we look at the L2 Dirichlet space and the multiplier algebra of the L2 Dirichlet space. So for this infinite set of functions Gj in the Dirichlet space, we say this capital G is in the L2 Dirichlet space. The following norm is bounded. So the norm is just the same as the Dirichlet norm, except replacing the absolute values with L2 norms. And for capital F equal to this vector of functions from the multiplier algebra of the Dirichlet space, we say that capital F is in the multiplier algebra of the L2 Dirichlet space, and we define the row operator, the row multiplication operator, MFR, as just row multiplication, taking on elements from the L2 Dirichlet space and takes those elements to the Dirichlet space. And similarly, we define column operator MFC, which is just column multiplication on the elements of the Dirichlet space and takes them to column vector in L2 Dirichlet space. So the following theorem for the multiplier algebra of the Dirichlet space is given by Benjade and Trent in 2015. So it's basically an analog of Wolff's ideal problem, now on the multiplier algebra of the Dirichlet space. So we assume that we have these conditions A and B satisfied, and that implies that there exists a G in the multiplier algebra of the L2 Dirichlet space with bounded operator norm such that FGT is equal to H cubed. And note that A implies FF star is less than or equal to 1, and B is just like in Wolff's ideal theorem, right? So next we try to determine what conditions imply ideal membership of H, which was a question posed by Trent. And so that is the main theorem that I'm working on and that I'll be outlining shortly. So we have these the same condition A and a slight change to the condition B, where you see the exponent is changed to 3/2 instead of 1/2, and an additional condition on an additional boundedness condition on H prime will imply the existence of this G in the multiplier algebra of the L2 Dirichlet space with bounded operator norm, satisfying FGT is equal to H. So H is in the ideal generated by the FJ, right? So the proof of the theorem follows the same structure as Wolff's proof of the Corona theorem, and we want to construct G in the multiplier algebra of the L2 Dirichlet space such that FGT is equal to H. Douglas lemma shows the existence of a bounded L2 Dirichlet function UH where row multiplication by F gives HH is equivalent to the existence of a bounded operator C taking the Dirichlet space to L2 Dirichlet space where row multiplication by F gives HH, right? And then a commutant lifting argument will provide a G in the multiplier algebra of the L2 Dirichlet space such that the operator C is just column multiplication by G, and thus the conclusion follows. So first we have a reduction to a D-bar problem, and we try this initial guess UH for little h in the Dirichlet space, and see easily that row multiplication by F gives us h. And of course, as we might have expected, d bar is not equal to 0, otherwise that would have been too easy. Alright, so we consider adding a function, say w, such that the range of w is equal to the kernel of f, and adding the function will make h analytic. Right, so it will satisfy our d bar equation. D bar is equal to 0. So again, we see that because, of this fact that range w is equal to kernel f, MFR UH is going to be equal to HH. And then our d bar of UH is equal to 0. Now, if and only if d bar of W is equal to this thing on the right-hand side here, right? So we can construct a queue with entries either 0 or plus or minus fj, such that f star minus f star f is equal to q star. And that equation will imply that range of q is equal to kernel of f. So the following construction of Q is given by Trent in one of the references. It's easy to see in the finite case. First, we'll see for n is equal to 3, we have Q as this matrix here. Really easy to show that FQ is equal to 0 there, and that equation is satisfied. Similarly, for n is equal to 4, we have this similar kind of setup here, right? And then in the infinite case, Q is constructed in a similar manner, where it's constructed out of these matrices AK, where, again, we see this similar pattern as in the finite case. And it's really not much work to see that QQ star is equal to this FF star minus F star F. And so we do have that the range of Q is equal to the kernel of F. Right, so part 2, we solve the d bar equation. Well, this new d bar equation where we replace this f star minus f star f with this q star. Right, so to solve this d bar equation using the Cauchy transform like we did in Wolff's proof of the corona theorem, we need the right-hand side to be smooth across the boundary of the unit disk. So we will replace f and h with fr and hr, where r is 1 over 1 plus epsilon is some small positive number, so that fr and hr are smooth across the boundary of the disk. In particular, they'll be smooth on the disk of radius 1 plus epsilon. And we can also make this initial assumption that h is an analytic polynomial, because the analytic polynomials are dense in the Dirichlet space. Now, using the Cauchy transform, we can define W and see that the d bar equation is satisfied, right? So with UH defined, we can move on to part 3, which consists of a lot of integral estimates. Again, we are looking at this L2 Dirichlet norm here, which is the same as the Dirichlet norm, replacing absolute value with L2 norms, and a lot of lemmas that will show this boundedness, right? And finally, part 4 is the conclusion of the proof. So given the L2 Dirichlet function UH, Douglas' lemma gives the existence of a bounded operator CR from the Dirichlet space to the L2 Dirichlet space, such that the product of the F multiplication operator and CR is equal to HRH. And given the CR, the Commuton-Lifting theorem gives GR and the multiplier algebra of the L2 Dirichlet space, satisfying the conclusion. And then, of course, we want this to be, we want to drop that smoothness assumption. And so we can use a compactness argument and convergence in the strong operator topology to prove the conclusion holds, right? Just taking R to 1. Really taking epsilon to 0. Right, so that's it, and here are the many references. Thank you for listening, and I hope you enjoy.